On a calm afternoon in August 2021, off the coast of southeast Alaska, a small research boat lowered an underwater speaker into the sea and played a single recorded sound into the darkness below. It was a humpback whale contact call, the closest thing to a whale saying, "I'm here." The team had captured that exact recording only a day earlier, in the same waters where a pod of humpbacks had been feeding, including a female named Twain, first identified back in 1987 near Hawaii, and sighted in these Alaskan waters dozens of times since. There was a real chance the scientists were about to play out Twain's own voice back into the ocean and ask her a question in her own language. For a few tense minutes, nothing happened. Then Twain surfaced, swam straight toward the boat, circled it slowly, and began to call back. Every time the researchers replayed the contact call, she answered again. A sound went out. A response came back. Another call. Another answer. For 20 straight minutes, a wild whale and a boatload of humans appeared to take turns speaking to each other. The scientists had deliberately built pauses into their playback, spacing the calls the way whales naturally do, and Twain waited through every single pause before responding, never once talking over them. That detail is what turned the encounter from a strange anecdote into something the scientific world had to take seriously. If she was simply reacting to noise, the timing wouldn't have mattered. Instead, she seemed to understand the rhythm of the exchange itself, know exactly when to stay silent and know exactly when to answer, the same unconscious choreography that governs an ordinary human conversation. Dr. Brenda McCowan of UC Davis, who led the study describing the encounter, called it the first documented exchange of its kind between humans and humpback whales using the whale's own communication system. The research was published years later in December 2023 in the journal PeerJ, co-authored by Dr. Fred Sharp of the Alaska Whale Foundation and Dr. Lawrence Doyle of the SETI Institute. But the moment itself, the 20 minutes on that boat, is where this story really has to begin, because it forced scientists to ask a question they had circled for decades without ever fully committing to. What if whales are not just making noise? What if they are actually saying something? And what if humans have simply never had the tools to listen closely enough to notice? If you're already hooked, hit subscribe now, because what happened after that Alaska encounter is where the story turns from a single strange moment into a scientific race involving artificial intelligence, cryptographers, linguists, and nearly 10,000 hours of recordings pulled from the darkest part of the ocean. None of this happened by accident. The real groundwork had been quietly laid years earlier in the offices of the Radcliffe Institute for Advanced Study at Harvard, where marine biologist David Gruber was spending a fellowship year in 2017. Gruber wasn't even thinking about whales at first. He was working on soft robotics designed to gently study jellyfish, trying to convince people that these strange, drifting creatures deserved more attention than they got. Almost nobody was interested. Then Gruber came across the work of biologist Shane Garrow, founder of the Dominica Sperm Whale Project, who had spent years recording the clicking calls of sperm whales in the Eastern Caribbean. Gruber began playing some of those recordings on his laptop in his office. One day, a cryptographer named Shafi Goldwasser, also a Radcliffe Fellow that year and a winner of the Turing Award for her work inventing zero-knowledge proofs, happened to walk past his open door and hear the clicks drifting out into the hallway. She stopped and told him something that changed the direction of his entire career. "Those sounds," she said, reminded her of Morse code, and she asked whether he had ever tried running them through machine learning. Gruber hadn't. Nobody really had. Not seriously. Whale researchers had spent decades recording, cataloging, and studying whale behavior, but almost nobody had approached the clicks as if they might be an actual structured communication system with grammar-like rules underneath. Goldwasser introduced Gruber to another Radcliffe Fellow, Michael Bronstein, a specialist in deep machine learning who would go on to become a professor of artificial intelligence at Oxford. The three of them kept talking long after that year at Radcliffe ended. In 2019, they returned to Harvard for a 2-day seminar that pulled in biologists, roboticists, linguists, and machine learning experts from around the world, all wrestling with the same outlandish question. Could artificial intelligence actually help humanity understand what a sperm whale is saying? By the end of the second day, the group had reached a kind of quiet consensus. It might actually be possible. The following year, with funding from the TED Audacious Project, that seminar became Project CETI, short for the Cetacean Translation Initiative, and it built its base of operations on the island of Dominica in the Eastern Caribbean, chosen specifically because certain sperm whale families returned to those same waters generation after generation. These weren't anonymous whales passing through open water. Researchers already knew which families belonged together, had tracked their relationships across generations, and had even given names to many of the matriarchs leading these pods. If sperm whales had real, structured communities, this was clearly one of the best places on Earth to study them. Dominica itself turned out to be a deliberate choice, not a convenient one. The waters around the island sit close to a steep underwater drop-off, giving sperm whales quick access to the deep squid hunting grounds they depend on, without forcing researchers to travel far offshore to find them. Shane Gero had already spent well over a decade there before Project CETI existed, tracking individual whales by their tail flukes and the unique dialects of clicks used by different family units, building a catalog of relationships that most marine research projects never get the chance to assemble. That existing foundation is part of why Dominica became the natural home base once Gruber, Goldwasser, and Bronstein needed somewhere to actually test their ideas rather than simply theorize about them. What came next is what actually changed the picture. Project CETI installed networks of underwater microphones throughout the surrounding ocean and built specialized suction cup tags that could be temporarily attached to individual whales. These tags did far more than record sound. They tracked diving depth, water pressure, body orientation, and subtle physical movement, all while separating out which specific whale was making which specific click, even when several animals were vocalizing at once. In other words, the team wasn't just gathering raw audio. They were gathering context: who was speaking, who appeared to be listening, and what was physically happening in the water at that exact moment. That context is what gives artificial intelligence something to actually search for, because a system trained only on disconnected sound has nothing to compare against. Eventually, researchers fed close to 9,000 of these recorded codas, the short rhythmic bursts of clicks that make up sperm whale communication, into a battery of machine learning models built by a team at MIT's Computer Science and Artificial Intelligence Laboratory. For decades, the working assumption in whale science had been that sperm whales relied on a fairly limited vocabulary, something in the range of 20 distinct click patterns, each tied loosely to a specific social context, not unlike a small set of traffic signals. The AI results, published in May 2024 in the journal Nature Communications and led by MIT researcher Pratyusha Sharma, told a strikingly different story. Instead of roughly 20 patterns, the system identified 156 distinct codas, a number roughly 7 times larger than what scientists had comfortably assumed for years. And the deeper discovery wasn't just the raw count, it was that these codas weren't fixed, rigid signals at all. They contained layers that whales could adjust in real time, the way a musician might play the same basic melody slightly differently each time, while it stays recognizably the same tune. Researchers describe 4 separate components working together: rhythm, the basic pattern of spacing between clicks; tempo, how fast or slow the clicks were delivered; ornamentation, extra clicks inserted into a sequence that shift its overall shape; and rubato, tiny timing stretches borrowed straight from musical terminology, where a performer speeds up or slows down a passage for expressive effect. Put together, these 4 features let whales combine a relatively small set of basic building blocks into what could be an almost unlimited number of distinct messages, in a way that genuinely resembles how humans combine individual sounds into an essentially unlimited number of words and sentences. There's a specific scientific term for that phenomenon, and it's one that used to be considered a hallmark of human language alone. It's called duality of patterning, the idea that a small set of individually meaningless elements can be combined and recombined to build a far larger set of meaningful signals. Researchers on the SETI team, including Gruber himself and co-author Shane Gero, have said openly that once you start looking at sperm whale codas through this lens, you start seeing a level of structure that's hard to unsee. It doesn't prove that sperm whales possess language in the full human sense. Nobody on the research team claims that. What it does show is that their communication system has an internal architecture far more complex than anyone confidently assumed even 5 years ago, and that assumption had held for decades without serious challenge. Then came a second discovery that made the story even stranger. Researchers noticed that individual whales didn't communicate identically with every other whale they encountered. The same animal would subtly shift its vocal patterns depending on who exactly was listening at that moment. Think about how naturally humans do something similar without even noticing. People speak differently to small children than they do to other adults, differently to close friends than to unfamiliar authority figures. Constant, mostly unconscious adjustment based on the listener is baked into ordinary human speech. Scientists call this pattern audience design, and it matters because adjusting your communication for a specific listener generally requires some understanding that the listener holds a different perspective, different information, or different needs than you do. In cognitive science, that capacity connects to something called theory of mind, the ability to recognize that other minds exist separately from your own, with their own internal experience. Whether sperm whales possess anything resembling theory of mind is still an open and genuinely contested question, but the presence of audience design-like patterns in the CT data is exactly the kind of evidence that pushes researchers to take the possibility seriously, rather than dismiss it outright. None of this is the first time whale communication has hinted at something bigger than instinct. Long before machine learning entered the picture, historical records had already suggested something unsettling about how whales share information across enormous distances. In the middle of the 19th century, American whaling ships pushed deep into the North Pacific, hunting sperm whales for the oil stored in their massive heads. In the earliest years of that expansion, hunting was brutally efficient. Then, within just a couple of years, something changed. Marine biologist Hal Whitehead of Dalhousie University, working with whaling historians, dug through tens of thousands of digitized logbook entries covering more than 75,000 days of voyages, and found that the success rate of harpoon strikes on sighted whales dropped by roughly 58% within about 2.5 years of whalers arriving in a new region. That decline couldn't be explained by the easiest, most vulnerable whales simply being killed off first, and it couldn't be explained by early crews being unusually skilled, because their success rates elsewhere in the world were nowhere near as high. Something else was happening. The whalers themselves wrote about it constantly in their own journals, describing whales that seemed to warn each other, flee upwind where sailing ships struggled to follow, or actively defend one another during an attack. Whitehead's research concluded that sperm whales, which live in tight, kin-based social groups, were very likely learning defensive behavior from each other and spreading that knowledge with startling speed across entire regions, faster than any single ship could physically travel between those waters. If that conclusion holds, it means sperm whales were sharing urgent, potentially life-saving information across their social networks more than 150 years before anyone thought to ask whether whales might be capable of anything like language at all. Whitehead's team tested several competing explanations against the logbook data using statistical models, including the possibility that whalers simply grew less careful about recording failed hunts over time, and the social learning explanation consistently fit the actual numbers best. It also raises an uncomfortable question about what the earliest structured signal scientists might eventually decode could actually turn out to mean. If whales really were passing warnings about human violence through their social groups back then, there's no reason to assume they've stopped. And no reason to assume that whatever pattern eventually gets decoded first will turn out to be something comfortable. One of the more striking findings buried in decades of whale research involves how young sperm whales actually learn to communicate in the first place. They aren't born already knowing the local dialect. Like human children learning to speak, they have to practice, repeating clicks imperfectly at first and slowly refining them over years, mostly while their mothers dive to hunt in the deep water below. One of the earliest things a young sperm whale appears to pick up is something researchers call an identity coda, a specific click sequence that marks which social group, or clan, that individual belongs to, something close to a family name broadcast into the water. What stands out is the order in which these skills develop. Social identity gets absorbed before a lot of practical survival skills, before deep diving technique, before serious hunting ability. From essentially the beginning of their lives, these animals are wired to understand who they are and who they belong to before almost anything else, built on a communication system that existed for millions of years before any human ever suspected it was there to be studied. Researchers studying these family units in Dominica have documented distinct vocal clans, each with its own signature style of coda, coexisting in the same waters without ever fully mixing their dialects, the way neighboring human communities might speak mutually understandable but clearly distinguishable versions of the same language. A calf raised in one clan grows up hearing, and eventually reproducing, the specific rhythmic signature of its mother's family group, reinforcing group identity across generations long before that calf understands anything else about the wider ocean around it. If this is changing how you think about whales, subscribe now, because the strangest layer of this whole story hadn't even been discovered yet when Project CETI first published its 156 coda breakthrough, and it came from an entirely different kind of researcher looking at the problem sideways. While the MIT team focused on rhythm, tempo, and timing, a linguist at UC Berkeley named Gasper Begosh, who serves as the linguistics lead at Project CETI, took a completely different approach. Instead of analyzing the spacing between clicks, he slowed the recordings down and studied their internal acoustic structure the way a linguist studies human speech sounds. What he and his colleagues found, published in research that built directly on the 2024 phonetic alphabet paper, was something nobody expected from an animal with no vocal cords, no tongue, and no lips in any form resembling ours. Buried inside individual clicks were spectral patterns that closely resembled human vowel sounds, structured, discrete, and repeatable across different whales. The team identified two distinct patterns. An ah sound similar to the vowel in the word father, and an e sound closer to the vowel in the word see. Even more surprising, they found gliding transitions between the two, the whale equivalent of what linguists call a diphthong, the same kind of smooth vowel shift that happens in the English word boy. Begosh has since said publicly that the whale communication system, which had always sounded like some kind of alien code, started to look a lot less alien and a lot more familiar once his team slowed it down and really looked closely. That's a genuinely strange thing to sit with. Human vowels depend on an extraordinarily specific piece of biological machinery, a lowered voice box, a flexible tongue, careful jaw control, and resonance chambers in the throat that took millions of years of evolution to develop. Sperm whales have none of that. Their entire sound-producing system evolved for something completely different, an enormous oil-filled organ inside their head called the spermaceti organ, working together with structures called phonic lips, originally built purely for echolocation, the same basic principle bats use to navigate total darkness. And yet, according to researchers, a system built entirely for hunting and navigation may have ended up carrying something that behaves remarkably like the vowel structure underlying human speech. Scientists have a name for two unrelated species independently landing on similar solutions to similar problems: convergent evolution. Humans and sperm whales split apart on the evolutionary tree tens of millions of years ago, evolved in completely different environments, and ended up with completely different bodies. And yet, if these findings hold up, both species may have arrived at communication systems that share a surprisingly similar underlying architecture. Begush has pointed to earlier work on elephant vocalizations as part of what reframed his thinking, since elephants, another large-brained, socially complex mammal, also produce low-frequency calls with structure researchers are still working to fully map. Seen that way, sperm whales aren't an isolated curiosity. They may be one data point in a much broader pattern of large-brained animals independently developing structured, information-dense communication wherever evolution gives them the social complexity and the physical means to produce it. The raw power behind the system responsible for these sounds is difficult to fully grasp. Sperm whale clicks have been measured at roughly 230 decibels underwater, making them, by most measurements, the loudest sounds produced by any animal on Earth. For comparison, a jet engine at takeoff registers somewhere around 140 to 150 decibels in open air, and sustained exposure to sound in the 180 to 200 decibel range is considered dangerous enough to seriously injure or kill. The gap between a jet engine and a sperm whale's click is not small. It is enormous, and because the decibel scale is logarithmic, every additional 10 points represents roughly a tenfold increase in raw intensity. At close range, that kind of acoustic energy can move through soft tissue almost like a physical shockwave. And divers who have experienced sperm whale clicks up close have described sensations ranging from temporary numbness to chest pressure and unexpected warmth spreading through the body. Now consider what that actually means when you put it beside the linguistic findings. The exact same biological structure capable of producing one of the most physically powerful sounds on the entire planet is, at the very same time, apparently capable of producing subtle, layered, vowel-like communication patterns detailed enough to draw comparisons to human speech. Raw physical force and structured communication exist side by side inside a single organ, shaped across millions of years by one of the harshest environments any animal has ever had to survive in. Out of the 156 identified codas, one particular sequence keeps reappearing across different whale families and different social contexts far more consistently than random chance would explain. Rather than acting as a single isolated signal, it appears to be woven into something closer to a recurring phrase carrying genuine social weight across sperm whale society as a whole, though researchers are still careful to say they do not yet know what, if anything, it actually means. That admission matters, and it's worth repeating clearly. Every scientist directly involved in this research, from Gruber to Sharma to Begush, has been consistent about one thing. Identifying structure is not the same as understanding meaning. Finding 156 distinct codas, 4 combinable acoustic dimensions, vowel-like patterns, and audience-sensitive shifts in delivery tells us the system is far more intricate than anyone expected. It does not yet tell us what a sperm whale is actually trying to say, or whether saying is even the right word for what's happening beneath the surface. Some of the researchers involved have been careful to frame their work using the same lens applied to the search for extraterrestrial intelligence, treating sperm whales as a genuine test case for how humans might one day try to interpret a completely unfamiliar, non-human communication system, one shaped by an environment and a set of senses almost nothing like our own, and possibly the closest analog to alien contact that anyone on Earth will get to study firsthand for a very long time. Which brings the story back to where it started, out on that boat off the coast of Alaska, with a whale named Twain circling a research vessel and answering call after call for 20 uninterrupted minutes. That encounter didn't decode a language. Nobody involved claims it did. But it demonstrated something that had never been documented so clearly before, that a wild humpback whale could recognize the structure of a human-initiated exchange, follow its rhythm, and respond to it in a way that mirrored the basic mechanics of a conversation, wading through silences instead of talking over them, matching intervals instead of ignoring them. Combine that with what the Dominica research has found in sperm whales, the 156 codas, the rhythm and tempo and rubato and ornamentation stacking together into something resembling duality of patterning, the vowel-like spectral structures gliding into diphthongs, the audience-sensitive shifts in delivery that hint at something like an awareness of the listener, and a picture starts to take shape that would have sounded like science fiction only a decade ago. Whales may possess communication systems built from the same fundamental design principles that underlie human language itself, developed independently across tens of millions of years of separate evolution, in an environment defined by darkness, crushing pressure, and near total silence to the naked human ear. And there's a genuinely uncomfortable layer sitting underneath all of it. If the very first structured signals scientists can point to with real historical confidence are tied to 19th century harpoon strikes, to whales going suddenly silent near a wounded companion, and then producing altered, more urgent vocalizations that seem to ripple outward to other pods, that is not a friendly greeting. It looks a great deal closer to a warning passed at scale, decades before anyone thought to take the possibility seriously. Nobody recorded those early moments carefully enough to know for certain what was being communicated. The whalers who heard them assumed it was simple panic and moved on with their work. Modern researchers, sitting in Dominica with hydrophones and machine learning models, or drifting quietly off the Alaskan coast with an underwater speaker, are approaching the same fundamental mystery with tools nobody had access to even 15 years ago. What they're finding is a communication system considerably richer, more structured, and more deliberate than science was prepared to accept. The work is far from finished. Project CETI's own researchers describe this as a multi-year effort that will likely require millions, possibly billions, of recorded codas before any confident translation becomes realistic. And they've said as much publicly, rather than overselling where the science currently stands. Researchers openly acknowledge they've only begun scratching the surface of what these patterns might mean, and every scientist involved is careful to distinguish between finding structure and understanding meaning. But for the first time, there's a serious, peer-reviewed, evidence-based case that something far more sophisticated than instinctive noise has been happening beneath the ocean's surface for millions of years, hidden from a species that only recently developed the tools to start listening properly. If that turns out to be true, then one of the oldest ongoing exchanges of information on this planet has been happening in total darkness the entire time, and humanity is only just now beginning to catch the first few words of it. If this changed how you think about whales or about what might actually be happening beneath the surface of the ocean, drop a comment and tell me what you think that recurring, still undeciphered coda might actually mean, and subscribe, because researchers are still working through thousands more hours of these recordings, and there is almost certainly more to come.